Today we're going to go through what the main emissions of a natural gas engine are and how they're produced. So starting off, the main emissions of a natural gas engine are nitrogen gas, N2. Air is 78% nitrogen gas, and most of this passes right through the engine. Carbon dioxide, CO2, this is one product of combustion. The carbon in the fuel bonds with the oxygen in the air. Water vapor, H2O, this is another product of combustion. The hydrogen in fuel bonds with the oxygen in the air. These emissions are mostly benign, although carbon dioxide emissions are believed to contribute to global warming. But because the combustion process is never perfect, some smaller amounts of more harmful emissions are also produced in engines. Carbon monoxide, CO, a poisonous gas that is colorless and odorless. Is carbon monoxide bad for the atmosphere? No, it's not. Is carbon monoxide bad for human beings? Yes, it is. Carbon monoxide blocks the ability of your hemoglobins to be able to carry oxygen out to your muscles for your body to use. Carbon monoxide in the atmosphere dissipates within 48 hours. If you filled the room with carbon monoxide and you came back 48 hours later, there would be no carbon monoxide in the room. It would all convert to carbon dioxide. Okay? It's one of the easiest emissions to reduce, is carbon monoxide. Hydrocarbons, or volatile organic compounds, called VOCs, or referred to as VOCs, produce mostly from unburnt fuel that evaporates. Sunlight breaks these down into forms of oxidants which react with oxides of nitrogen to cause ground level ozone, or O3, a major component of smog. One of the other VOCs is formaldehyde, HCHO. We're seeing a lot of regulation here in the United States on formaldehydes, and they're proving challenging to reduce on lean burn engines. Nitrogen oxides, NO, nitrogen oxide, and NO2, nitrogen dioxide, together are called NOx. So when you look at NOx, it's NOx. So then N is nitrogen, O is oxygen, and the X is a variable. That means we don't really know how much oxygen has been attached to it, but we make the assumption that NO and NO2 are the primary NOx being produced from the engine. This contributes to smog and acid rain and also causes irritation to the human mucous membranes. These are three main regulated emissions and also the ones that catalytic converters are designed to reduce. Pollutants produced by an engine. In order to reduce emissions, modern engines carefully control the amount of fuel they burn. They try to keep the air-to-fuel ratio very close to the stoichiometric point, which is the calculated ideal ratio of air to fuel. Theoretically, at this ratio, all of the fuel will be burned using all of the oxygen in the air. The stoichiometric ratio for natural gas is 17.2 to 1, meaning that for each pound of fuel or natural gas, 17.2 pounds of air will be burned. The fuel mixture actually varies from the ideal ratio quite a bit during load changes. Sometimes the mixture can be lean, an air to fuel ratio higher than 17.2, and other times the mixture can be rich, an air to fuel ratio lower than 17.2 to 1. Okay, so some of the different stoichiometric ratios, natural gas is 17.2 to 1. Propane is 15.5 pounds of air to 1 pound of fuel. Diesel is 14.1 pounds of air to 1 pound of fuel. Gasoline is 14.7 and ethanol is 9 to 1. So now you can see why natural gas, when we convert an engine from diesel or gasoline to natural gas, you can see that natural gas takes up much more space than the gasoline or the diesel fuel. Therefore, you literally can't get your bang for the buck out of the cylinder. Okay, your volumetric equations are off. Okay, air, just in a generic weight, is 1.2 ounce per cubic foot, and natural gas is 0.78 ounces per cubic foot. That being said, that tells us that natural gas is lighter than air. It's harder to fill that cylinder with the natural gas than it is with the air. Okay, therefore it takes up a lot more space than gasoline or diesel fuel. Gasoline is 6.2 pounds per cubic foot, and diesel fuel is 7.1 pounds per cubic foot. And going back to the natural gas, it's only 0.78 pounds per cubic foot. So with natural gas being 0.78 ounces per cubic foot, it takes up 127 times the space of gasoline for the same weight. Therefore, it's very hard to charge a cylinder with enough to make a good burn. Oxygen. What is air? Air is a mixture of several gases that are invisible and odorless. It consists of 78% nitrogen, 21% oxygen, and then less than 1% of argon, carbon dioxide, and other gases. That being said, the 78% nitrogen has absolutely no value to an internal combustion engine. Matter of fact, that 78% nitrogen is where your NOx is coming from. Some of the things on an internal combustion engine that can change are valve timing, compression ratios, things like that. Some of the very simple things, let's look at where carbon monoxide comes from. When air and fuel come into a cylinder, the air and the fuel are mixed. And if you have a cold combustion and you have too much fuel, you'll produce a lot of carbon monoxide. Okay? If you have early combustion and high cylinder pressures, therefore high cylinder temperatures, you're going to produce a lot of NOx. Other things in the cylinder, or the characteristics of an engine in the cylinder, are you have cylinder wall squelching. When the gases are mixed together, they're ready to burn. If you had the absolute perfect carburetor in the whole world, or fuel injection system, and your air and fuel could be mixed perfectly, it is not possible for that engine to consume all of that fuel and air. The reason being is temperature. Your cylinder walls are cold, your piston's cold, your valves are cold, and any of the gases that are mixed and are together and are next to the cylinder walls, or any of the cold metal components, don't burn. They partially burn. So therefore you have oxygen and fuel, unburned hydrocarbons, going out the exhaust at that time. The hotter the engine runs, the less unburned hydrocarbons you have. The colder an engine runs, the more unburned hydrocarbons you have. Therefore, you always need to have your engine warmed up before you start testing emissions. So now in this slide, this is showing us uncontrolled engine emissions. Okay? To the left of this line is rich, to the right is lean. One of the things we need to understand at this point, though, what is excess air ratio, or lambda. Okay? This says 1 right here. Remember we were talking about the stoichiometric value, 17.2 to 1 for 1 pound of air? If we had an absolutely perfect burn and we were consuming all of the air and all of the fuel, that would be considered a lambda of 1. A perfect burn. Nothing would be left. Okay? That's literally impossible to maintain or reach, but for the sake of the graph, we have a lambda of 1 here. Okay? Now anything over here is going to be considered a lean burn engine. Anything over here is considered a rich burn engine. Typically, when an engine comes from, say, Caterpillar or Waukesha, and they were designed not to run with a catalyst, they're going to be a little bit above a lambda of 1. One of the things we notice is right up here on the NOx, that's where we produce the most amount of NOx. That's also where an engine produces the most amount of horsepower. That's because you're getting the best thermal energy out of that fuel that you're putting in the engine. Okay, you're getting the best consumption of it. But with that being said, when nitrogen is heated up and under high pressure, we produce a lot of NOx. So when we add a catalyst to a rich burn engine, we have to richen the engine up. In other words, we give it more fuel and the carbon monoxide starts to come up. But as soon as we do that, the NOx drops down. Okay? Now we're going to drop this down into a lambda of about 0.97, right in here, where our NOx and our CO are about a 2 to 1 ratio. Actually, it's going to be on this side of the line. 2 to 1 ratio. Our CO will be about twice the parts per million as our NOx. And in just rule of thumb, and that's where the catalyst is going to operate at its optimum. Okay? If we continue riching the engine up, the carbon monoxide is going to go up. By richening up, I mean more fuel, more fuel. less air. This blue line is our oxygen, and as we richen it up, it just keeps getting lower and lower. There's less and less oxygen. Therefore, the temperature is dropping and our NOx is dropping because we have less and less oxygen available because the fuel is consuming it. Okay? As we lean that engine back out again, the catalyst will quit working right around in this lambda of 1 for a rich burn. The catalyst will quit reducing NOx. Okay? As we lean it out, the NOx goes higher and higher. And now on a lean burn engine, as we start to lean that engine out farther and farther and farther, the NOx comes down and down. This comes to a point where the NOx actually gets lower than the carbon monoxide. Now, this is the reason that the industry started leaning towards lean burn engines. The graph is laid out, but it's not really in true proportion. We would look at this, and on a rich burn engine, we would be putting out about, in the ballpark of 5,000 parts per million CO and about 2,500 parts per million NOx. When the manufacturers started leaning the engines out, they learned that they could lean this engine out and they could get the emissions down low enough at the time to run the engine without any fuel management systems or exhaust after treatment on it at all. These numbers over here, our carbon monoxide was probably in about a 500 range, 500 parts per million. And our NOx was probably about 150 to 200 parts per million. And as the industry has advanced, these numbers keep getting pushed down lower and lower. So say the Caterpillar lean burn 3600, that engine's going to run over in the ballpark of 30 to 50 parts per million NOx without any treatment on it, and it's going to run less than 500. Typically they run about 200 to 300 parts per million CO. But emission standards have continued to drop, and now these guys have had to add on oxidation catalyst, different than the catalyst that is added here, which is a three-way catalyst. Okay? What is Lambda? Lambda is the actual or operating air-to-fuel ratio divided by the stoichiometric or perfect combustion air-fuel ratio. A lambda of 1 is perfect combustion. A lambda greater than 1 is lean. A lambda of less than 1 is rich. So the way I lay this out typically on the board is I will assume an engine runs at 10 to 1. We're going to make up our own numbers for easy math. If I ran an engine at 10 to 1, meaning for every pound of fuel I was putting in 10 pounds of air, makes for easy math. If that engine was using 15 pounds of fuel, or excuse me, 15 pounds of air for every pound of fuel, that would be a lambda of 1.5. If we were running 5 pounds of air to every pound of fuel, that would be a lambda of 0.5, half of what the actual is. Okay? And that's typically where I draw it out on the board and do the math, and then they understand it there. An example would be if stoichiometric air-fuel ratio was 10 to 1 and the engine was running at 15 pounds to 1, 15 pounds of air to 1 pound of fuel, the lambda would be 1.5 or 15 to 10. Okay? Other things that affect the emissions of an engine are valve timing. It is extremely critical to have your valve timing correct on an engine. Most camshafts are designed for an engine to run at 1 RPM. We can all take the analogy of when you get your muscle car or whatever, one of the things you do, or your Harley Davidson, you go out and you put a big camshaft in it. What does that do? What does it do for you? Other than makes it sound good at the stoplight, it really doesn't do a lot other than now you can turn a higher RPM. So what does this all mean? So let's start here. The intake valve opens. The intake valve opens actually ahead of top dead center. Okay? So let's follow that around. So your piston is going down. Your piston was still coming up right here. Now it reached top dead center, and now it's walking itself down. It's pulling it in. It's actually drawing in air and it's drawing in fuel that are mixed together. And we reached bottom dead center. Now it doesn't seem logical when you think like a syringe. If you were pulling that piston down, think of a syringe. It's coming down, and you've reached the full travel on the syringe. Or in this case, the cylinder. The cylinder isn't necessarily charged because of the speed the piston is dropping. It takes more time to fill that cylinder. So because of air has mass, mass has inertia, and that's going to carry in. It's going to continue to carry, even though the piston is starting on its way back up, the air is still rushing into that cylinder. Then when they equalize it, when the air quits flowing, they want to shut that valve to charge that cylinder as much as they possibly can. The faster you run the engine, in other words, the higher the RPM, the more overlap you can have, excuse me, not overlap, but valve duration you can have, okay? Now let's continue on. We've closed our intake valve. Now the piston is coming up. It came up to top dead center. We fired the cylinder just a little bit before top dead center, and now we've started bringing that piston down. The expansion, the thermal expansion of the gases are pushing that piston down. But once we reach about 10 to 20 degrees after top dead center, absolutely no more than 30 degrees, we've lost all of our efficiency with natural gas. So as this piston starts to go down, what's one of the things we do? We get just past 90 degrees, in this case here 46 degrees on this cam card, and we open the exhaust valve. Why do we open the exhaust valve before it reaches the bottom? Okay, well the purpose that we do that for is when we open that exhaust valve, that allows the exhaust gases to rush out so that when the piston is starting to come back up, it's not pushing gases out. And it also sets us up for the next sequence of the exhaust flow and the flow through the top of the combustion chamber. So now our exhaust gases are exiting the chamber, they're exiting, and look what happens. We open the intake valve. The intake valve is open and so is the exhaust valve. Why do we do that? The reason we do that is called purging the top of the cylinder or scavenging. You had exhaust gases that started racing out right here. Well, they're going to continue to flow because they have weight. They're going to flow out, and as they flow out the exhaust, they're going to suck in the new gases, and it scavenges or purges the top of the cylinder with clean gases and get rid of all the spent gases. Okay, and we just start the process over again. So that being said, a cam is designed for a specific RPM by the way the intake and the exhaust valves open, when they open, okay, and how much overlap there is. If you get too much overlap, what happens is if you have a carbureted engine, the exhaust gas or the mixed fuel and air come in and they end up going out the exhaust before they ever get a chance to burn. In other words, you purge the top of the cylinder too much. Now where are those going to burn? Those are going to burn in the exhaust between this exhaust valve and the turbo, or if it's not turbocharged, they're going to end up and make it out to the catalyst, and they'll make it out to the catalyst on a turbocharged unit as well, and they'll burn up your catalyst. And all that combustion is going to take place on the catalyst. Anything that's not consumed in this process ends up out on the catalyst. We got to keep this as low as we can. Okay? All right. Ignition timing has a very large impact on emissions in an engine. Okay? So we'll look at this chart, and down here you see negative work and positive work. This right in the middle is top dead center. Okay? So we're going to light the fire. Our spark is going to go ahead of top dead center. Why is it that we light the spark ahead of top dead center? Because it takes time for the fuel to burn. Flame propagation. It takes time for that fire to get going and those exhaust gases to heat up. At the same time, your piston was still coming up at this point. Okay? Now, let's imagine this. This is the perfect right here. Okay, we lit the fire, our power curve came up, our cylinder pressures are coming up real nice, and then as the crankshaft is rotating and the piston is dropping down, our cylinder pressures are dropping down just perfect. So we got a really nice burn here. We should be running that approximately 3,500 to 5,000 ppm CO, and we should be running between 1,500 and 2,500 parts per million NOx right here. Okay? What happens if our timing's too late? Well, our cylinder pressures are really low and we don't get a good clean burn. So then what happens is as our pressures go down, then all of a sudden the thermal gases expand. We don't produce any NOx. We produce real low amounts of NOx because we don't have any heat, and we've consumed all of our oxygen with that fuel with late timing and real low cylinder pressure. So right here we'll have high carbon monoxide and low NOx. Okay? This right here will have a nice combination, a 2-to-1 ratio of our carbon monoxide to our NOx. Now let's look at if we light the fire too early. Let's say we went 40 degrees ahead of top dead center, or 35 degrees ahead of top dead center. We're igniting really early. The fire is going to light, but then all of a sudden our cylinder pressures are built up and they start to be real erratic, extremely erratic. Pressures are all over the board. This is going to push our NOx and our CO up. Our NOx and CO are going to be very erratic. These lines represent cylinder pressures. One of the things that happen when you do this, you can start to cause detonation. Detonation and pre-combustion are the same but different. Detonation is when you lit the fuel at the top of the cylinder and the piston is coming up, and now it acted like a diesel, and with the thermal gases expanding at the top of the cylinder and the pistons coming up, now the rest of the gases ignite all at once or ignite very erratically like a diesel engine would. When we're down here and our timing is correct, the flame propagation is all one direction and it's nice and uniform as the piston is dropping down out of the way. Okay? Pre-ignition versus detonation. Pre-ignition is typically caused by carbon or, again, early timing, but detonation is when they act like a diesel and start the pressure building up with the piston still coming up, and then the rest of the gases explode at one time. How do we measure emissions? Okay, we use grams per brake horsepower hour. Okay, what in the heck does that mean? Grams per brake horsepower hour, sorry. Grams, this is how it's spelled out when you see it on your permits. Okay, we can use that to convert it to pounds per hour, tons per year, or any weight increment that you want to. Okay, what does this mean? Grams per brake horsepower hour. Well, if we break it down, it sounds complicated, but it's not. Grams is a weight. Okay, if we had a 1 gram engine, right here, grams to 1 gram engine, and horsepower, here's 1 horsepower, 1 hour, 1 hour, that would be a 1 gram of pollutant if that was a 1 gram engine. So let's think about how this works. Grams is weight. Okay? Brake horsepower is performance. How much work did we get done? And this is time. Okay? Now the thing we have to understand here is horsepower. What the heck is horsepower? We don't have dynos out on these units. We have to extrapolate what the horsepower is doing. Okay? Typically, that's done by knowing how much fuel was going into the engine. Okay? So if we had a 1 gram permit and we had a 100 horsepower engine, in 1 hour, you could produce 100 grams of pollutant. Okay? James Watt came up with the horsepower calculation, and his horsepower, 1 horsepower equals 33,000 foot-pounds per minute. In other words, they could pick up 33,000 pounds when a horse walked for 1 minute. They would pick up 33,000 pounds 1 foot. That's how they calculated horsepower. How much natural gas does it take to make 1 horsepower? Ultimately, that's how we're going to determine how much horsepower we're using, by using engine manufacturer specifications and how much fuel does it take to make 1 horsepower. 100% efficient is 2,545 BTUs per 1 hour. That's at 100% efficient. No engine is 100% efficient. Richburn default is 9,400 BTUs per hour to make 1 horsepower. tells you how inefficient a rich burn engine is when it comes to converting fuel into horsepower. A lean burn engine default is typically around 8,600 BTUs per hour. A lean burn engine is more efficient in making horsepower out of the fuel that is given. Horsepower as it relates to BTU. Horsepower can be defined as 2,545 BTUs to make 1 horsepower in 1 hour. However, most of the available BTUs in the fuel are wasted as heat exiting in the exhaust. For an engine to produce 1 horsepower in 1 hour, it consumes approximately 10,000 BTUs. This value is a very useful tool for determining regulator and fuel delivery piping sizes. You can also determine when you're out on location, just off the cuff, how much horsepower is being made if you have a fuel flow meter for that location. You can look at the fuel flow meter and know approximately how much horsepower you're utilizing. Actual fuel consumption ranges between 7,000 BTU and 10,000 BTU per brake horsepower hour. This down here is very key to remember. The lighter an engine is loaded, the less efficient the BTU to horsepower conversion is. So, in other words, work the engines hard, they convert the fuel into horsepower much better than if they're lightly loaded. You'll get a lot better emissions on an engine that has got a good load on it versus an engine that does not have a good load on it. Okay? One of the ways we determine it is by using GURP on a Caterpillar engine. Caterpillar provides us with some information that makes it much easier to determine what that horsepower is. We don't have to assume defaults of 9,400 or 8,600 BTUs for the rich or the lean burn. Okay? So when you pull up a GURP sheet from Caterpillar, you can look at the load. Okay? And as you're looking at this load, brake horsepower on this particular engine is a 3306B, okay? It's an 1,800 horsepower engine, aftercooler, water jacket. You can look at all the specs all the way down. It's a catalyst setting engine. Exhaust oxygen is at 0.3% oxygen, okay? Well, we know this is a little rich burn Caterpillar 3306. So now, it's capable of 203 horsepower at full load, okay? At full load, we can see its efficiency is 8,100. It's actually a very efficient little engine when we have a full load on it. For a rich burn engine, that's great. Okay, as we drop in horsepower to 75% at 152 horsepower, look at our fuel consumption per horsepower, brake specific fuel consumption. The brake specific fuel consumption goes up, and we get down to 50% load. We know that it's extremely inefficient at 9,310 BTUs per brake horsepower hour, and when it was loaded, it was 8,100 BTUs per brake horsepower hour. Okay, and we can do it in standard cubic feet, or we can do it in BTUs. Okay. Now, if we look at a 3516 Caterpillar, which is a lean burn, this one's going to run at 1,400. Compression ratio is 8:1, and so was the rich burn on the 3306B was 8:1. Okay, but we're gonna turbocharge the heck out of this thing. We're gonna push a lot of air into it, and for a lean burn engine, we're gonna push the NOx level down to 0.5 grams per brake horsepower hour. Okay. Now let's look at this. Per brake horsepower hour, we're making 1,380 horsepower on this particular 3516. And when we look at the fuel consumption, it's clear down around 7,301 BTUs per horsepower being produced. Okay, if we drop clear down to 50%, we can look again. That's going to be 690 horsepower, and the fuel consumption now jumps way up to 8,399. So you're always better to use factory specifications if you have them. In the US, the EPA defaults to those 9,400 and 8,600 retrospectively when you don't have performance data for the engines. Always best to have the actual performance data from the manufacturer. Okay? Just an interesting piece of information. It takes 641,186.5 calories to make 1 horsepower in 1 hour. Okay. All right, so now to convert those grams to brake horsepower hour, we know that it takes 28 grams to make an ounce, 16 ounces to make a pound, and 2,000 pounds to make a ton. That way that's how we convert our grams into pounds per hour or tons per year. Okay, typical emissions tests being done. You have a sample line going into the stack. We call this a shepherd's hook normally, and this sample line is heated to prevent any water from condensating from the high temperature exhaust gas, and as it goes into this line and cools down, they don't want the water to drop out because that impairs the NOx reading when you have exhaust gases being pulled through water or water settled into lines. Okay, a couple of different types of analyzers. The one on the left here is an ECOM analyzer. They're both chemiluminescence, both these analyzers. This one is a testo, and cells are made in England for them. There's several different analyzers out on the market. They all have their good points and their bad points. This is the ECOM. The good points about them is their software seems to be very good and very user-friendly and easy to use. The drawback to them, the cells in them don't take much punishment at all. They tend to fail in high VOC, high unburned hydrocarbon environments. The cells will saturate and they'll either ruin the cells, or the cells will take quite a while to air out till the next day before you can use it again. And those cells are typically in the $500 a piece, so you don't want to be messing them up. And it only takes a few minutes to ruin one. So this should always be using an analyzer. Same guy should use it, or the people using it should always be trained. The Testo 350, very robust analyzer. It'll take a lot of punishment. Great analyzer for field mechanics, and the information is very accurate coming off of these as well. But the software is a little bit less user-friendly, is what my opinion is on it. So, okay, this is what it looks like when they pull an FTIR lab, Fourier transform lab, out onto the location, and they can pull their VOCs, their NOx, and their carbon monoxide, and other exhaust constituents can all be measured. The portable analyzers typically won't do any unburned hydrocarbons or VOCs. So you can't do a complete test if you're required to do VOC testing. You have to have an FTIR on location. Okay, typical look of inside of a lab. Okay, why do I need a catalyst in fuel engine controls? Okay, here's a little example. This example is one I put together several years ago. It's 100 horsepower. I just kind of used the Caterpillar 3306 information. And on this 100 horsepower uncontrolled engine, it starts out about 6,500 parts per million CO, which equals 17 grams per brake horsepower hour. At 100 horsepower equals 1,700 grams per hour. Divide that by 28 grams to get an ounce. You get 61 ounces an hour. Take that times 24 hours, and that equals 1,464 ounces per day. Divide that by 16 ounces to get pounds, and you get 91.5 pounds per day. Times 365 days a year, that's 33,397 pounds per year. Divide that by 2,000 to get tons, and you get 16.5 tons of carbon monoxide off that little 3306 that's been running 24/7, 365. Okay, and we can run through the same equation with the carbon, or with the NOx. Excuse me, NOx is a little bit heavier, so it doesn't take as much to get the weight there. So here we're only starting at 2,200 parts per million. That equals 10 grams per brake horsepower hour. When we run through the equation, we get 9.7 tons per year. Using the same math, we come up with 7 tons per year for hydrocarbons. This little uncontrolled 3306 cats is making about 33.2 tons per year of exhaust pollutants. Now, what happens when we add a catalytic converter to this? Okay, if we add a catalytic converter and an air-fuel ratio controller to the engine, now, and we drop the emissions down to 0.5 grams per brake horsepower hour, which is a pretty standard emissions in the United States for non-attainment areas. That took that number from our 33.2 tons per year down to 1.228 tons per year. That's a pretty significant reduction in emissions. So that's why we run a catalytic converter and an air-fuel ratio controller. What is a catalyst? A catalyst is a substance that affects the rate of reaction without itself being consumed by the reaction. Generally, they increase the rate of reaction, but they can also slow down the rate of reaction due to the change in the specificity of the reaction. Okay, let's break this down into something simple. Everybody's worked with concrete. If you have some concrete aggregate, some rock and sand, in other words, and then you have some fly ash and some concrete powder, and you mix it all together, it does absolutely nothing. It just is dirt and sand and rock and some fly ash and cement powder. But we have to add water to that concrete, okay? If we add water to that, we start to build heat. Things start to happen. It says here, generally they increase the rate of reaction. If we didn't add water to the concrete, nothing would happen. But now we've added water, and then if we continue on, but they can also slow down the rate of reaction due to the change in the specificity. Well, right now we're talking about the increase in the rate of reaction. If we look at the description of a catalyst, the catalyst is a substance that affects the rate of reaction without itself being consumed by the reaction. So when we think of concrete, when we added the water does not stay with the concrete, but it changed everything around it. Okay? So when we had the rock, the aggregate, the sand, the fly ash, the cement powder, we had nothing until we add the water. But the water itself was not consumed by the reaction. When the concrete's done setting up, there's nothing there. It's very similar to the way a catalytic converter works on an engine. You can also slow down the rate of reaction on a catalytic converter as well. If you plug it up, you get antifreeze on it. There's different things that slow down that rate of reaction. Okay? There's a lot of different shapes when it comes to catalysts. There's a lot of different manufacturers out there. There's octagonal, there's round, there's rectangular, there's octagon with a bonnet, there's round with a bonnet. A lot of different shapes. Okay? If a catalyst is brand new, sometimes you can tell whether it's an oxidation or a three-way catalyst. Oxidation catalysts will typically have a little bit of a brown or a goldish hue to it. And an oxidation catalyst are typically got a darker brown or darker black color. Once they've been run, you can't tell that. Now, how is a catalyst made? Well, we start out with ferritic stainless steel. Ferritic stainless steel is magnetic. You can stick a magnet to it. It'll attach to the magnet, whatever you would like. Okay, that's how the properties on this foil oxidize. The foil is really thin. It's about 2 thousandths thick is all that foil is. Very, very thin. So we have a flat sheet, and then we take another flat sheet and we run it through a set of dies, and that corrugates that foil and it starts to roll it together. In years past, this was a standard way of manufacturing the catalyst element, but there were a lot of challenges related to this due to telescoping. The foil would come unraveled. Wouldn't sustain backfires very well. So what happened over the years is nickel was laid in between the foil. So stainless steel is a real high nickel content. It's got iron properties in it so that it'll oxidize. And as we roll it up, the foil goes over top of the nickel is rolled up within it, and then once the catalyst is completely made and made to the diameter it's needed, then it's put in an oven and heat treated. At that time, this nickel sweats out like solder or brazing and welds all these high points together and makes it a solid or a rigid substrate. Makes it very strong. No more coming apart or failing during backfires or telescoping from heat in the center. Okay, so the corrugation is typically an equilateral triangle. Okay, so both sides of this are the same. All sides of the triangle are the same dimension. That's how we get a lot of square footage in the foil itself. We get a lot of surface area so that we can attach our wash coat. So the bottom sheet, this is 2 thousandths thick. This foil is 2 thousandths thick. This is 2 thousandths thick. We add the top sheet. It seems like it'd be restrictive, but this is a 90% open area. There's not much restriction there. It takes an awful lot to plug a catalyst up. When you do plug a catalyst up, you know you've got some pretty serious issues. Okay, it's just a slide with the brazing, showing the brazing, the importance of where it's bonded together and how much stronger it makes it. This is just a slide to tell you that an unbrazed catalyst, if you laid it on a table, it would take 461 pounds on a 14.5-inch catalyst to start separating that catalyst, and you had it pushed down overhanging it or to separate the catalyst. If you had a brazed substrate and you had it hanging over the edge of a table halfway, it would take 3,120 pounds to break that. These are the benefits of a brazed catalyst element versus an unbrazed catalyst element. Okay, this is what 300 cells per square inch look like. Doesn't seem possible, but there's 300 cells per square inch here. Okay, closer look, you can see the foil where it's stacked up. You can see where it's brazed. All of those contact points are brazed together with the nickel, called rigid substrate. Okay, what do we put on the catalyst? Well, when the catalyst was in this state here, the catalyst had no wash coat on it at that point. Okay, the catalyst was just stainless steel. It wasn't going to do anything for you. Big spark arrestor. But then we use a mixture of platinum, palladium, and rhodium. These constituents are ground up microscopically fine, or these precious metals are ground up microscopically fine and then put into a slurry or a wash coat where they can be spread out across the catalyst foil. Okay, why do we use platinum, palladium, and rhodium? Why don't we use something else? Well, when you think about it, platinum is white gold. All of these things are very corrosive resistant. They withstand high temperatures, and they each have their own properties when working or reacting with the exhaust gases. Okay. If we took a really close look at the foil, this would be our 2 thousandths thick foil, and this would be our wash coat. And mixed in that wash coat are these microscopic particles of the precious metals. What are some of the things that damage a catalyst? Well, there's a lot of things that'll damage a catalyst. If we get it really hot, over 1250 degrees, what happens is this alumina wash coat starts to collapse. It's the carrier. The precious metals are still there, but it traps the precious metals in an area where the exhaust gases can't get to it. So the precious metals are still there. Nothing happened with them. They're able to react just fine, but the gases are not able to get to them. I always make the analogy, think of a styrofoam cup. If you heat up a styrofoam cup too much, it'll collapse into almost nothing. You still have all the styrofoam there, but it isn't doing any good whatsoever. So these areas here are areas where the exhaust gases can migrate through and make contact, and these are called sites. And the more and more we heat it, the less and less sites that become available. The catalyst is still functioning at this point, but it's not functioning the way it was when it was new, before we melted the wash coat of the alumina. Okay? Sintering is when you get it really hot. When you get it hot enough that you've melted the precious metals, and now your platinum, palladium, and your rhodium have all bonded together. They are worthless at that point. You have no surface area. You have not enough areas to make contact. Okay? The precious metals, active metal, precious metals, or base metal elements which are active in the combustion reaction, platinum, palladium, and rhodium. These metals are known for their purity, their high melting points, and their ability to stay stable at high temperatures. In addition to their stable oxidation and reduction properties, they are also extremely resistant to corrosion. Platinum and rhodium are effective in reducing NOx. Platinum and palladium are effective in oxidizing CO and VOCs. Platinum is more poison resistant, palladium is more thermally stable. So the idea behind mixing these three items, you can mix the three items, you can have more platinum and rhodium, and you'll reduce NOx. If you had platinum and palladium, you're going to reduce CO. If you want a catalyst to reduce NOx better, you're going to add a little more rhodium to it. Okay? If you want it to reduce CO, you're going to add a little bit of more palladium to it. Platinum is more poison resistant. What do we mean by poison resistant? Poison resistant means we can take on things like cyanide, which will kill almost any catalyst. Ethylene glycol or antifreeze destroys a catalyst very quickly. So you get engine oil additives, you get things in the gas that are coming into the engine, and platinum is going to stand up to that a little bit better. Palladium is going to be more thermally stable. In other words, in the higher temperatures, it's not going to react quite as crazy as the platinum would. Okay, the rhodium, that's based in there, that's added into the catalyst on any three-way catalyst so that you can reduce the NOx. What determines how a catalyst is made is usually how well they react, what you're trying to achieve for your emissions reduction, and then the third party into that, or the third player into that, is always the cost of the precious metals. One catalyst manufacturer versus another. You can play games with these, with the mixtures on these, and you can make a catalyst that works really well when you first put it in, but if you don't have enough platinum in it, it's not poison resistant and it'll die quickly. Or you can play games like you can put it in and have a very thin wash coat and expose a lot of the precious metals, and they'll react very well. But the sites are spread out in a thin wash coat, and the more sites that you lose due to sintering, to overtemping, or to poisons, the quicker the catalyst will degrade. And if you start out with a catalyst with more of the balance of the precious metals on it, it's going to last much longer. That being said, they're typically more expensive. Catalyst elements. There are three-way, or NSCR, that's non-selective catalytic reduction, is for a rich burn engine. Oxidation catalyst is for lean burn engines. Oxidation. If an electron is lost, then an oxygen will be gained. Platinum and palladium reduce CO and VOCs. Redox or reduction oxidation. If an electron is gained, an oxygen will be lost. Platinum and rhodium reduce NOx. Back to this slide. NOx is the hardest thing you're going to be able to reduce on a rich burn engine. And you can't reduce it on a lean burn engine outside of post-catalyst treatment like SCR, selective catalytic reduction. When an engine isn't set up correctly, this becomes the first thing that fails. Your NOx reduction fails the quickest. If you have exhaust leaks, if you have misfires, if you have anything that's increasing the oxygen content in the exhaust gases, you will fail to reduce your NOx. We have to use up all of the oxygen. It says here, if an electron is lost, an oxygen will be gained. So when we're reducing carbon monoxide, CO, we need free oxygen to turn that into CO2, carbon dioxide. So we use up all of the free oxygen from the carbon dioxide, or making carbon dioxide, and we get that oxygen right here. Once we've used up all of the free oxygen, this is how our NOx is reduced. It goes after this oxygen right here. The carbon monoxide was still very active in looking for oxygen to convert to CO2. When you used up all of the free oxygen or excess oxygen in the engine, then it starts to reduce the oxygen that was attached to the nitrogen. If you have an exhaust leak again, even a pinhole in an exhaust system will stop that reaction from happening. You'll end up having very low carbon monoxide levels because you had available oxygen to convert it to carbon dioxide very easy. But you are not able to reduce this. The reason being is nitrogen is very stable. It takes a lot of temperature to get nitrogen to be unstable. Carbon monoxide, on the other hand, by the time it reaches 450 degrees, you won't get any more reduction. It won't become any more unstable. So it's very easy to reduce carbon monoxide. Carbon monoxide starts to reduce at ambient air temperature. Believe it or not, it will convert on its own at ambient temperature if there's oxygen available. Again, like I mentioned earlier, if you took a room and filled it with carbon monoxide, CO, and you came back a day or two later, that room would only have carbon dioxide because of the available oxygen in the atmosphere. So until that carbon monoxide uses up all the free oxygen, you can never reduce the oxygen that's attached to the nitrogen. Much more stable situation. Okay, there's nitrogen atom. Here's just a layout of the oxygen and reduction oxidation, or oxidation and reduction oxidation. So you have a reducing agent, this is your catalyst, comes together, then it gets oxidized, this is your compound in the middle. An oxidizing agent, reduction, gains an electron, gets rid of an oxygen, and so then NOx is reduced. Okay, NSCR is a term that we use for non-selective catalytic reduction, abbreviation, acronym, whatever you want to call it. In the presence of oxygen, the oxidation of CO and VOCs are preferred. Like we spoke earlier, CO and VOCs will oxidize very easy when there's oxygen in the presence of it. Therefore, in order to get NOx reduction, you have to limit the amount of oxygen that is available in a catalyst. This is a Richburn we're talking about now. Typically, exhaust oxygen levels between 0.3 and 0.5% to obtain appreciable NOx reduction. And then you need the temperature between 500 and 1,000 degrees to achieve the maximum reduction rates. Typically, you get over 450 to 500, the catalyst isn't going to reduce carbon monoxide much better. Okay, there's what a carbon monoxide, one carbon, one oxygen. Okay, NOx, you got nitrogen and oxygen, and here you've got one nitrogen and two oxygen, NO2. Okay, formaldehyde, HCHO. Okay, combustion products, catalyst reaction. Okay, we're going to go through the three-way catalyst or Richburn catalyst. Another name for the Richburn catalyst is NSCR, non-selective catalytic reduction. Okay. Now, one of the things that's always in an exhaust stream is oxygen. Okay. And we were talking earlier, you have to limit your oxygen in your exhaust stream to 0.3% and no more than 0.5%. Okay. That's going to go into the catalytic converter. Okay. Now, the next thing that goes in that's always in your exhaust stream is carbon monoxide, carbon and oxygen. It typically goes in, we're going to use numbers of 5,000 ppm. Okay, it can be 5,000, could be 3,500 to 5,500, even 6,000. And depending upon what your emissions permit are and how well your catalyst is working is going to determine where those numbers come down to. But let's assume it's 5,000 parts per million going into the catalyst. Okay, and then our NOx, Again, oxides of nitrogen is going to go in, and let's assume that's half of that, a 2-to-1 ratio at 2,500 ppm going in. Then the last thing we want to think about is our temperature. All right, last slide. Okay, on our temperature on a rich burn engine, that can vary quite a bit from a little naturally aspirated 3306. You might have a hard time making 500 degrees. Or you could be on a 7044 Waukesha and they're running 1350 coming off the turbos, which is pretty hot. 1250 is probably a little more normal. But optimally, we're going to shoot for that 800 degrees going into this catalyst. Okay? Now, for carbon monoxide to turn into CO2, it's going to use this oxygen right here. Okay? So when we use that oxygen up, what's going to come out on this side is 0% oxygen. Okay? That oxygen got used up on this to make CO2, but this will strip down, and at a 96% reduction, that'll come out around 210 ppm, maybe 220. Okay, that'd be a 96% reduction. That'd be typical. On our NOx reduction, if we see that and we're getting a 96% reduction, we used up all of this oxygen. There's no more oxygen left. Okay, so now for CO to continue to reduce by turning into carbon dioxide, it's going to need this oxygen right here. Okay, when that goes into the catalyst and goes through it, it will come out at about 110 ppm. Okay, when this happens, we're going to see an exothermic reaction. So if we came in at 800 degrees, we could easily be coming out between 50 and 100 degrees higher. So it could be 850 degrees Fahrenheit to 975 or 1,000 degrees coming out. Okay? That's that temperature rise. That's like when we were talking about the concrete earlier. You have an exothermic reaction. You get a temperature rise across the catalyst. The harder the catalyst works, the more this temperature is going to go up. So in other words, the more carbon monoxide you put into the catalyst, or VOCs, the higher this temperature is going to get. Okay? All right, let's put in some different scenarios here. Let me erase this ink on this slide. Okay, let's go back to here, and let's say we were doing our 0.3% oxygen going into that catalyst, okay? And our CO was 5,000. And our NOx was 2,500 ppm. Okay? And our temperature was 800 degrees again. What would happen if we had an exhaust leak? Let's say we have a very small pinhole. We got an exhaust manifold gasket leaking, or maybe a wastegate gasket leaking, and we were leaking 0.2% of oxygen. So we put this up to 0.5%. Let's go to 0.7% oxygen. A very, very small leak. Here's what's going to happen. Last time we came out this side, we had 0% oxygen. We're still going to get 0% oxygen. We might see a slight increase, like 0.02%, but not very typical. What happens on our CO? Well, before we were getting a 96% reduction. We're going to increase that reduction. We were coming out about 220 before. Now, we could easily be coming out 100 ppm or less. Okay? Why is that? That's because you had more oxygen and you could make more CO2, and this is free oxygen. Okay? So it didn't have to work so hard to take this oxygen. Nitrogen is stable. So what's going to happen on our NOx? Well, the CO didn't need any more oxygen, so guess what happens here? This could easily come out at 2,500 ppm. And your only thing wrong is you had 0.2, maybe 0.4% oxygen increase ahead of the catalyst, and that stopped your NOx reduction from happening. What happens on the temperature? Temperature's still going to come out that 850 degrees to 1,000 degrees. That part will remain the same. Okay? Let's go through another scenario. What happens when the engine is set to rich? Okay, we'll erase this. Okay? Same thing, if the engine is rich, let's say we're at 0.2% oxygen. We're using up all the oxygen in the combustion process because we're putting up a lot of fuel into it. We know for certain we're going to have 0% on this side. Okay, downstream of the catalyst. But what happens when you set an engine rich? What happens to your CO? Your CO was typically 5,000 on the engine we just explained earlier. What happened if this turned into 8,000? Okay? And if we were going to do a 96% reduction on 8,000, 96% reduction on 8,000 is going to be about 320 ppm. Okay? So we could have easily failed a test or been right up against our limits if it was a 1 gram test because the engine was running too rich. When that engine's running rich, what happens then? Our NOx on this same engine that was 2,500 before could easily be 1,500 going in. Okay? We've got a lot of oxygen, we've got a lot of carbon monoxide, we're using up all the oxygen. We need to turn a lot of that carbon monoxide into CO2. We could come out of here at 50 ppm on NOx. Okay? That's what happens when we set the engine too rich. To the parts per million count, what happens on the temperature? The temperature gets interesting. As you add VOCs, unburned hydrocarbons, and carbon monoxide, and you started out at 800 degrees, you could easily jump up to 1,000, 1,200 degree on the downstream side. So that's an increase of 200 to 400 degrees. That's too much. Anything over about 125 to 150 degrees increase across the catalyst in your temperature means you've got issues. The catalyst is working too hard for it at that point, and you're going to cut the catalyst life short. Like we explained earlier, the aluminum wash coat's going to collapse, and the precious metals are basically going to drown within the aluminum wash coat, and not be available to make an active site available to the exhaust gases because it's completely coated and submerged in the alumina. Okay? So now another example would be what happens when the engine is set to lean. We'll go ahead and erase everything on the slide. I erase everything on the slide, and then we'll start over. What happens if we have an engine that's set to lean? Okay, we'll lay that scenario out. If we get an engine that's set to lean, that means our oxygen is going to be increased. Typically, on a rich burn engine, we want to see that 0.3 to 0.5%. Okay, we're going to stick with the 0.3 right now. What happens? We go to set to lean and we're at 0.7%. It has the same effect as if we had an exhaust leak. But this time when the engine is set lean, it's our oxygen, when the engine is set lean, our CO could drop. It was 5,500. It'll drop drastically, and maybe it starts out at 2,500. Okay? Our oxygen is still going to get reduced, but we don't have near as much carbon monoxide being turned into CO2 to utilize this extra oxygen content. But we don't have a lot of CO. It's going to come out of there. It could easily come out at 50 ppm or less. Okay? Because we didn't start out with very much and we had plenty of oxygen to make CO2. Now if we are NOx though, this is where it gets tricky. Our NOx on a lean running rich burn engine is going to increase. So maybe it was normally 2,500. This could easily jump to 3,500. That'd be pretty high, but just for explaining this, this could easily come out with the extra oxygen at 3,500 on this side of the catalyst. Maybe 3,000, maybe you'll get just a tiny bit of reduction. This means the engine's too lean. Our CO is low and our NOx is high. Okay? And our temperature, typically in this situation, if we came in at 800 degrees, we could easily come out at 750 degrees. We could have a temperature loss across the catalyst in a lean environment because you deactivated the catalyst. Okay? You're not working it very hard. And you deactivated the NOx reduction with your excess oxygen. Okay? That explain anything? Another scenario on this. Another scenario would be if you had a single cylinder misfire on an engine. I'll go ahead and erase all the information on this slide. Let's say you had a single cylinder misfire. Things are going to act a little bit funny with a single cylinder misfire. You get on these larger engines, a 7044, 3516, rich burn. It's difficult to hear a misfire unless you were standing next to it or you're a super mechanic. Okay? So we'll start out, our oxygen is going to be a little bit high because we have a misfire and that oxygen wasn't consumed, but it may not be too high. Let's call it 0.07%.
It's 4.
Let's go to single cylinder. Okay, you lost one cylinder. Say it's a 3516 rich burn. Okay. Say our oxygen content, because of the misfire and we weren't consuming the oxygen in that cylinder, although it's getting mixed in with the rest, it's going to be hard to see, but you might be 0.5%, maybe 0.7% again, but it's not a continuous oxygen and it's very hard to read. You're getting pulses from that one cylinder. Comes through here, you might be reading 0%. Maybe 0.02%, okay? But our CO is going to be a little high. Earlier we were showing 5,000. We might be running 6,500 with a misfire, okay? That's going into this catalyst. That's getting high. But the thing that we have is we have extra oxygen to go with that extra CO. Our NOx might be still right at that 2,500 range because we don't have any combustion temperature and we don't have any cylinder pressure on that misfire. Okay, our temperature going in probably 800 still, maybe even a little bit less, but let's stick with 800 right for this explanation. Because of our free oxygen, we're going to have a little bit of difficult time reducing NOx. So maybe our NOx is only dropping down to 500. Okay, but our temperature is going to be the telltale of everything. When you get a single cylinder misfire, you could easily reach 1200 degrees across the catalyst. You know at that time, when you're seeing this 400 degree rise across the catalyst, you know that you've got too much raw fuel, too much carbon monoxide, and too much unburned hydrocarbons, so to speak, going across the engine, across the catalyst, and as catalyst is combusting that within the foil, having a real high reaction rate, and your temperature grows exponentially. At that point, you're going to start burning up the catalyst. The catalyst surface is going to react first, and right shortly after the surface, it's going to start burning it up. Okay? This will conclude today's session. Thanks for watching. I hope we provided you some value today, and we'll catch you next time. Thanks, and have a great day.